is Dr. S.P. Arsa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, we are mainly discussing about the active vibration control, and in that, like we are discussing about the smart materials, that how these materials can really behave as a smart when they are treating as the sensor or the actuator or the entire, we can say, the control unit together. So, in this you see here, we discussed almost about the piezoelectric feature, we discussed about the ER feature, means the electro-rheological features in that particular fluidic part, and then we can straightway use as the vibration controlling feature. So, in the today's lecture, we are going to discuss about the magneto-rheological fluids. As we can see that in the the electro-rheological fluids have certain like the limitations towards that, and we will try to see that can they be overcome in this magneto-rheological fluid. And like there are certain excellent properties of this ER fluid, like they can be used straightway as the ER clutches, ER brakes, or even you see we can say that the electro-rheological vibration dampers can also be effectively used. Under there you see we can say either the shear modes or any kind of modes features are there. So, in the magneto-rheological fluid, as the name itself speaks, that we have again same the rheological particles are there, or we can say the properties of the particle, the rheological, and the magnetic field is being applied. So, it is a type of the smart fluid. In a carrier fluid, usually a type of we can say the non-conducting oil, and when it is being subjected to the magnetic field, the fluid greatly increases its apparent viscosity, and to the point it is becoming a viscoelastic solid. Importantly, the yield stress of the fluid when it is being active, we can say active means it is when it is on situation, the state can be controlled very accurately by varying the magnetic field intensity. So, the upshot of this we can say that is the fluid's ability to transmit the force can be straightway controlled with the electromagnet, which gives rise to its many possible control based applications. So, it's straightway you see what is the strength of the electromagnets are there, accordingly you see here it can that transmission force can be effectively controlled there itself. So, MR fluid, if we are just talking about you see when like electric field the electric field is applying and we are getting the apparent viscosity which is being increased right from liquid to solid, the same thing is happening here when the magnetic field is being applied, the apparent viscosity is being increased and then it is being forming from liquid to solid. So, how they are being different? So, MR fluid is different from a ferrofluid which has a smaller particle, and again the MR fluid particles are primarily on the micrometer scale and are to a dense for a Brownian motion to keep them suspended. That means you see here we need to check it out that it has to be suspended in the lower density carrier fluid. And ferrofluid particles are primarily the nanoparticles that are suspended by the Brownian motion and generally will not be settled under any normal conditions. So, we are going to discuss about you see that when we have the electro-rheological fluid or the magneto-rheological fluid, how you see the things are being different in these cases. So, the magnetic particles which are typically we can say of the size of micro or nanometer are just the spheres or the ellipsoids. So, when we have the ellipsoids or the spheres of the size of these nanoparticles, they can be suspended within the carrier oil and then are being distributed randomly as per you see like the viscous or any orientation feature. And also like when we have a normal circumstances, we know that the random orientation of these magnetic particles are pretty common in any kind of this conducting the non-conducting oil like the carrier oil. But when the field is on, means the magnetic field is being applied, even the microscopic particle may be from 0.1 to 10 micrometer range align themselves along the line of the magnetic flux. And when the fluid is like contained between the two poles, say you see like which is being separated in between 0.5 to 2 millimeter, there is a chain of the particles which restrict the movement of the fluid, and absolutely they are aligned perpendicular to the direction of flux, and that is why you see here there is an effectively increase in the viscosity of the part. And moreover, you see here the mechanical property of fluid when it is in the on situation, the states are anisotropic. Thus, a designing of this MR magnetological devices, it is crucial to ensure that these lines of the fluxes, the flux, whatever the lines are there, they must be perpendicular to the direction of motion which is to be restricted. So, say that we just want to restrict or we just want to put the resistance in one direction, the applied magnetic flux should be perpendicular to that direction only. Just like you see these, we have the carrier oil which is showing there you see by the green part, and we have the magnetic particles which are being randomly oriented. Now we want that they should be arranged in the column wise side, not in the row side. Then the particle which are being forming the chains in the direction of flux lines, you see here, these are you see like the direction of my magnetic flux which is just perpendicular to these lines, just perpendicular to these lines, and they are just forming the entire column wise structure. So, from the liquid to solid phase, we can simply see that when it is on, then we have a streamlined structure, and when it is like not on, then we have the randomly oriented structure, these fluidic particles. Or even rather you see, we can be even see here when no free field is applied, this is what you see the random orientation in which the carrier carrier fluid is there and these like the particles are there, and when the electric field is on, you can see that how the orientation is straightway changed, because now we want the resistance in this direction, the vertical column directions. Or even we can see on other way, when this is what you see like the change of pressure is there, when it is off, these magnetic, this MR fluid, and this is what you see we can say a laminar flow parts are there. So, there is a clear you see we can say a parabolic velocity profiles are there along with that when it is off. But when it is on, now you see that this is what my magnetic field lines along with that. So, you can see the orientation of along these like all the particles just align with this part, and we can say that you see at this part we have the shearing layer in which the shear stress which is more than the yield stress. And also we can say that this part which is being there, you see it is a just a plugging feature, and we can get straightway the shearing layer on just like a top and bottom. So, if you look at this with the perfect laminar feature, because of you see like the part here we have this part here straightway. So, on top and bottom the shear stresses are dominating there itself, the shearing mode. Or else even we are, when we are looking towards this part, when you have you see like the entire feature, the particles are being there and the carrier oils are there, straightway they are forming these columns or the chains along when the field is being applied. So, we can say simple example, one is the milk in which you see all the particles in the water which is a carrier form is being used just like randomly oriented, and when the magnetic field is on, the entire milk is being converted into the cheese. This is one way you see like through which we can simply explain that the liquid form of the fluidic nature, how it is being converted into the solid form in which you see like all the magnetic particles are being aligned and they are just showing the resistance in the direction where you see when they are being aligned there. When we want to see resistance in this column direction, we can simply put the column feature, or we want the resistance in this direction where the rows are there, we can frame the rows along these particular layers. So, this is the basic we can say principles which like we can straightway adopt it there. So, in case of magnetic-rheological fluid, a magnetic field which simply causes a chain like arrangement of the suspended particles by simply inducing a magnetic moment or the fluxes there itself. And they can also exhibit the yield stress which is being increasing with the applied field strength. And both we can say like a pre-yield region can also be characterized by the elastic properties, and the post-yield region can be characterized by the viscous properties. So, in like the Joly et al. Paper, they simply shows that when we just want to see the elastic and the like the viscoelastic the viscous feature, we can simply see that what exactly the yield, the pre-yield and post-yield regions are there, how the behavior is there. So, due to their qualitatively similar behavior, which is simply in a phenomenal mode of ER and MR part, we can say that these devices can be mostly like applied to either of the material. Now we are discussing about the modes of the operations. What are the basic modes in that? So, an MR fluid is used in one of the three modes of the operations where you see the direction features are being important. So, first mode is, we can say, the flow mode, or we can say sometimes it is a valve mode. Second mode, as we discussed previously, the shear mode. And third mode, in which you see the MR fluid is basically under operations, it is the squeezed flow mode. So, when we are talking about the flow mode, means the valve mode, the MR fluid is made to flow between the static plate by a pressure drop, and the flow resistance can be controlled by the magnetic field which runs normal to the flow direction. Then only it is being effective and we can get a proper resistance. Few of the examples of flow mode is the servo valves, dampers, shock absorbers, and even the actuators. In shear mode, the magnetic-rheological fluid is located between the surface moving, we can say rather the sliding or rotating surface, in relation to each other with the magnetic field, which obviously flowing perpendicular to the direction of motion with these shearing features. And the characteristic of the shear stress versus shear we can say rate, because when the shear stresses are being like there, the environment, the rate of shear strain is always being there with that, and it can be straightway controlled by the strength of this magnetic field. And the last mode, which is we are saying that the squeeze mode, the distance between the parallel pole plates changes, and when the distance is being changes, they are simply causing the squeezed we can say form with the magnetic particles. And in this mode, relatively high forces can be achieved, because when you are squeezing the things, the reaction features are being like quite reactive, and this mode is especially suitable for damping of vibration with the low amplitudes and high dynamic forces, because we know that when we are just going up to the few millimeters of the amplitude of this part, and even you see the forces are quite significant, this squeezed part can be effectively absorb the energy against that. And the squeeze mode has been used in some of the small amplitude vibration dampers because of its real operational features there itself. So, you can see that all three modes can be straightway shown there. When you have a flow mode, means the valve mode, you can see that they are absolutely, you see like moving in this way, and the pressure which is like the magnetic field which is being applied normal to it, and we can get, you see, like just the flow features. When you have the shear mode, as per the name itself, you see here they are being just like parallel to this, either in the rotational or any part, you see we have the shear force in that. And third, it is when you have the squeezed part, you see here the displacement is just they are just like changing the distance, and because of that you see the squeezing features are being occurred at the magnetic particle, and through that you see the high force with the low amplitude applications can be straightway occurred there. Or else rather we can simply explain with this way, when the MR fluid is being there, you see this is my applied magnetic field, and when we are just simply dragging in this direction the flow, certainly you see here they can be streamlined in this particular channel form. And when you have the shearing part, you see here this is what my motion, and this is, you see, so this is a parallel, or you see the rotating motion and the magnetic field which is perpendicular to this. we can get you see the shearing features at this particle path. Or else you see here, when the forces are being acting in this way, means when you see it is just squeezing, changing its like size between the two plates, we can get you see this is what the flow is, and you see the motion is like that, and we can get you see like the squeezing action there itself when we just want to see according to the application. Or even you see here with these particles which we are generally using, this is what you see the like the direction of this part, the flow part, and the vertical you see magnetic field is being applied in the flow, shear, or we can say this squeeze mode operations. So according to the action of these we can say magnetic the field or whatever the particle featured, the application of these various modes are being chosen. So flow mode can be used in damper and shock absorber with the use of the movement to be controlled to the force and flow through the channels across which the magnetic field is being applied. So this is a very smooth we can say part in which you see where we just want to absorb or to dampen out the vibration. This is one of the perfect part to be applied there. The shear mode, which is like we can say particularly useful in clutches and the brakes, and in places where you see the rotational motion must be controlled, it is perfect you see the shear motion, because you see here it is ultimately like putting the parallel forces in the rotation, or you see here in that particular sliding actions. And a squeeze flow mode is the most suitable application controlling the small, or we can say like the millimeter order movement, but involving the huge amount of the excitation forces. So this particular flow mode has seen, at least you see we can say investigation in various part where you see straightway we can straightway control the high excitation forces with the low amplitude feature. So MR fluid can be like applied successfully to the wide range of applications according to the service condition, applied features, and you see where we just want to control the entire say vibration or the excitation features. So the first, as far as the vibration control problem is concerned, they can be act as the damper. So MR dampers have clear object of intensive studies from both the point you see their interesting physical features, and also due to the potential applications to control damping in mechanical system. Because the essential characteristic of the MR fluids is their ability to reversibly change from free flowing linear viscous liquid to semi solid, having you see the controllable yield strength in millisecond. And when they are exposing to a magnetic field, they can be clearly controlled the yield strength even within the fraction of the milliseconds. So this is a pretty clear you see like we can say physical characteristic is there, in which you see we can say that they have clear ability to reversibly change right from free flowing to semi solid part, and this feature provides a simplest, quite rapid response interfacing between the electronic controls and the mechanical system motion part you see here. So these dampers are we can say new semi active devices which utilizes MR fluid to provide controlling damping forces, and these devices overcome many of the expenses and the technical difficulties which are being associated with the semi active devices. The design of this linear magneto-rheological damper is nothing but an actuator which allows controlling performance characteristic, in which you see we can say that the resisting force depends on the piston speed and the strength of the applied magnetic field. Because in that you see like working gap, whatever the particles are there, they are being like straightway provide you see the resistance according to their chain structure, but it is depending on that what exactly the piston speed is there and what is the strength of this magnetic rheological magnetic flux field. So these dampers can also be characterized by the large damping force, low power consumption, and maybe we can say used in various vibrating controlling systems. As you can see here, in this you see like we have the MR fluid here, we have the like the piston, because you see, as I told you, that it is straightway depending on the piston speed. So what exactly the piston speed is there, what is the flux, the strength of the magnetic flux, and with that you see here these like the magnetic this field under this like the electromagnetic coil, the strength can be provided, and these are what we can say the accumulator through which we can accumulate, or rather we can say that in this piston form there is a clear, you see, the magnetic flux which is being, like we can say, straightway applied, and this MR fluid which is there in between that can be straightway provide a good damping devices towards that. So this is what you see the basic like the arrangement in which we have the piston part. So how the piston, like what the movement is there, and then accordingly you see, according to the strength, this like the strength of this magnetic field, we can have a good damping featured in that. So when we are talking about, you see, this principle, the like as a damper part, we can simply go with the various mathematical models through which we can represent the mathematical function whose coefficients can be determined using the rheological part, that means the parametric value which are being adjusted until the quantitative results of the model are not closely matched with the data. So when we are talking about the damping part, the dynamic response of these MR fluid devices is reproduced by the semi-empirical relations, and then you see we can simply use the various parametric model through which we can justify the arrangement of mechanical elements in that, you see, like the spring or viscous disperse together. So the first model is coming under this magneto-rheological fluid damper is the Bingham model. As we discussed in the electro-rheological fluid, that when the fluid is being like under the shearing action, there are two features. It is not a Newtonian feature, there are two features. After the yield limit, there is a clear relation between the shear stress and the rate of shear strain. So you see here we have a clear Bingham nature there itself. So here also when we are applying the magnetic field on these like polarized particles, we can have a similar kind of relations. So most commonly behavior for this MR fluid is described by the Bingham plastic model. An ideal Bingham body behaves as the solid until it is reaches up to the minimum yield stress, say tau y. And when it is being exceeded there itself, you see here, then they are simply exhibiting the linear relation between the stress and rate of deformation or the shearing part. So this is one of the like relation for the Bingham part, that even we are applying the load up to certain limit, means before it is reaching to the yield point, they are absolutely, you see, the solid, nothing is being happening in that. But after that there is a clear elastic behavior is there. So we can say that it is something of viscous and elastic part. So they are almost similar to the viscoelastic feature of the materials. And then you see we can go with the same kind of, you see, the relation, that the shear stress tau which is being developed under the like action of these magnetic field with the nanoparticles, we can say tau is nothing but equals to tau y, that is my minimum yield stress, at which you see here there is a conversion from solid to liquid phase, or we can say to like non-Newtonian to like we have some kind of the linearity. So we can say tau is equals to tau y sine of this gamma dot plus neta gamma dot, where we know that the gamma dot is nothing but equals to the rate of shear strain, and the neta is clearly showing the plastic feature of the viscosity of the fluid. That is, we can say that the viscosity is having, you see, like at the zero field, which is simply exhibiting the Newtonian part. So we have a clear plastic viscosity, means the non-Newtonian feature of this. So we have both the tau y sine gamma dot, which is showing a linearity feature in the stress with the shear strain, and neta gamma dot is showing that rate of shear strain is there, but this is absolutely absorbed with the viscous plastic nature, or we can say like whatever the these solid features are there before the yield limit. So in the Bingham model we can say, if we are just going below the yield stress, then certainly, as I told you, the material is behaving like the viscoelastic feature, where we can say that the tau is proportional to the G into gamma. The G is not the shear modulus, the G is here the complex material modulus right now here, though it is the shear modes are there. So, we can simply define the shear strain and rate of shear strain within, you see, the like we can say the below yield stress. This relation is clearly showing that the MR material operate usually within the post yield continuously shear, or we can say flow regime. So, we need to check it out that what exactly the regimes are. What is the reason? It is below yield point or above yield point. If it is below yield point, then the tau is equals to G into gamma, and if it is above yield point, then certainly you see here we can say that this is absolutely showing the F equals to the same, you see, the linear behavior of that. So, you see, this is what you see the Bingham model, which is like giving in the excellent paper of the Spencer et al. You see here, in which it is there that whatever the forces which is being like excite the system just flowing in that, we have a clear C0 part, that is the minimum viscous part, showing the plastic viscosity there itself. And then you see here after that we have a clear proportion, the after yield point we have clear elastic features in that, in which we can say that it is simply like the tau y sine we can say like gamma dot, means we have the yield and we have, you see, the rate of shear strain is linearly varying with the shear stress part. So, you see here we can even put the mechanical analogy of such behavior with the column friction element, which is parallel just with the viscous dashpot. So, in this model, when we are just talking about the column friction features, in that the force F which is generated by this magneto-rheological fluid device can be obtained as the Fc sine of x dot plus C0 x dot, where we know that the x dot is absolutely the velocity part associated with the damping available and which is attributed to the external excitations, and the damping coefficient C0 and the frictional forces Fc are simply related to the fluid viscosity, and it is absolutely the field is depending on the yield stress respectively. So, this is what you see here, we have the two things together, we have the damping which is absolutely the function of the fluid viscosity, we have the frictional forces which depends on the field, that you see what exactly the yield stress fields are there together, and along with that you see here we are saying that this Fc means like the frictional forces is just varying with this sinusoidal feature, the sine omega or sine, you see, we can say x dot. So, when we want to represent the real character of these MR fluids, we know that the Bingham model, which is very close to that, is simply accounts for the electro or magneto-rheological fluid behavior beyond the yield point. That means, you see here, when fully developed fluid flow is there, or we can say if it is the whatever the shear stresses are there, if they are sufficiently high, then only we can say that we can just go for the real fluid behavior. But also we assumes that the fluid remains rigid in the pre-yield stress region. So, as you can see that on the diagram, this is clear that right from, you see, 0 to up to this point, the viscous part is so dominating that it is not exhibiting any kind of the flow part. So, whatever the energy which is being there, it is being dissipated or absorbed at that point, and you see beyond yield point, then this is a clear, this we can say the linear region, the elastic features are there. So, Bingham viscoelastic model for the MR fluid is clearly showing that if we have, you see, these Bingham models are there, then we need to show with this part first go straight, and then you see the linear propagation is there. And if you have the Newtonian fluid model, which can write from 0 to just proportion, they are absolutely showing, you see, the linear relations between this stress and shear strain part. Or else even when we are trying to see on the experimental features, then also with the flow and velocity, you can see that how the damping is being featured out here. So, this is what you see, this is the the green line is clearly showing that how you see the real variation is there in the force to the velocity or the movement for that part. So, when we are going with the MR fluid, there are various properties which are being documented by the Carlson and Zolli in their paper in 2000, in which we have the like with the typical MR fluid, we can get the minimum yield strength almost up to 100 kilopascal, where the maximum field can be there of 250 kiloampere per meter. The plastic viscosity, which is like the basic property before yield limit, can be like there 0.1 to 1 pascal into second, and it can be operated in the temperature range of almost, you see, we can say up to 150 degrees Celsius and minimum even up to minus 40 degrees Celsius. The response time is always less than milliseconds. That is the beauty of the system is. We can immediately get the response, you see here, when it is being acted there. The density is almost 4 gram per centimeter cube, and then you see when we are trying to relate the plastic viscosity with the like this yield limit, then we can have almost, you see here, 10 to the power minus 10 to minus 11 second per pascal, and then you see all other properties like the like all this power supply for this making all that part, you see here, is almost near about the 50 watts, and then we can get the maximum energy density like that. So this was the first model which can simply show the real character of the magneto-rheological fluid, which can be act as a damper also. Second, which is like further we can say that more refined part is the Bonch-Wann model. So Bonch-Wann model is just, you see, like we can say one of the most refined model, which is even like presented by the Spencer in their paper. And in this model, you see here, we just want to characterize the behavior of this MR fluid damper. So again, we need to reproduce the response of the hysteresis system to the random excitation. So we can say that we can straightway put a mechanical analogy of this Bonch-Wann model, in which you see here the force is generated by the device can be represented like this. Here we have the same, the spring feature, we have the damper feature together, but this is what you see the Bonch-Wann model, in which you see here we are saying that the displacement is y and the entire this like the total damper movement is xd. When the external force is being applied, there are three main devices which are being acted together according to the Bonch-Wann model, C0, K0, and you see this device in which we are saying that what exactly the hysteresis part is there in that. So these three like features in which you see we are just trying to consider, or we can say we just trying to put the response from the hysteresis system from the random excitations. So we can simply write the mathematical relations which can describe the Bonch-Wann algorithm for the MR damper behavior. So first is the primary displacement variable, say f, small f, which is nothing but equals to the C1 into y dot, means whatever the real character of the damper at that time which is related to, we can say it is all you see the damping parameters. So C1, if you look at C0 was the first damping, C1 was the damping which was, you see here, the outside part, and this C1 is related to the displacement y. So we have the damping force from the C1 is C1 y dot. So we have, you see, like when we are just trying to show the force in terms of that, we have the C1 y dot damping force plus restoring force is there due to the relation in between the xd, that is the like we can say whatever the variable features are there in the displacement part, and x0 is the initial part. So the difference of the damping and you see the initial part is just giving into K1, whatever the stiffness feature is there, is giving the restoring forces. And when we are going with the evolutionary variables, we simply account, you see, whatever the like the previous dependencies features are there, z dot is nothing but equals to minus gamma x dot d minus y dot into modulus of z into z to the power n minus 1 minus beta x by x d dot by like when we are just trying to compute these coefficients, again you see here the beta and this whatever the x0 which we are applying here, they are the constrained part. We are just trying to put the conditions. So, beta into x dot d minus y dot z to the power n plus minus a x dot d minus y dot n. So, we can say that you see we can straightway get these coefficients according to what the application means, where what the boundary conditions are there and what you see the operating features are there together. And the y dot which was there, you see like the initial first part, you see that what exactly the velocity component is nothing but equals to 1 by C0 plus C1, and C0 and C1 are nothing but the viscous damping parameters. And you see here we have it into alpha z, and alpha is nothing but the field variable which is absolutely depending on the applied voltage into z, and z you see, as I told you, that this is what the evolutionary variable depending on, you see like how the dependency features are there on the previous part, into C0 x dot d, because the C0 is just moving with the xd. So, we have the viscous forces with that, plus k0 into xd minus y here, because you see now the displacement which we are considering here is the y. So, these three equations which are being formed by the Bonk-Wenn is simply showing the relations of all these parameters when the entire fluid damper model is behaving under the excitation force F. And when we are trying to make the predicted part between the experimental and we can say like this theoretical part in the Bingham model, we can clearly like as I shown there, you see here, this is what my hysteresis slope when like the entire features are there in that. So, experimental features, as you see like it is a clear showing the nonlinearity when you see the green part when the experimental features are there. So, when we are going to the application of this MR fluid, then certainly first thing is coming in mechanical engineering, these damper of the various application have been there, and it is still you see the various like the compact and the robust features are being even added, and they can be used. So, these dampers are mainly used in heavy industries with the application, as you see the heavy motor damping, or we can say operator seat, or you see the cab damping in the construction vehicles, or there are various things where you see here the response time is required minimum, and there you see immediately we need to act these features. Even in the military and defense part, in which you see like the various researchers have been already put their efforts, and they are straightway using the fluid bullet resistance part in that, and the various all all-terrain vehicles which employed the dynamic MR shock absorber or the dampers are straightway using. The human prothesis, in which you see here the MR dampers are utilized in semi-active, the human prosthesis, in which you see here like whatever the leg features are there, they can be act as the integrated part in between that. Much like those in use in like used in these military or the commercial helicopters, a damper in this prosthetic leg can be straightway decrease the shock which is being delivered to the patient leg when it is being jumping or any dynamic actions are being happen. The sudden jump or sudden like we can say impactive force, which result in the increased with the mobility and you see like the agility for the patients. So, this is one of you see like the prosthetic feature in which you see like in the leg or somewhere you see when the dynamic actions are continuously being happen, the MR dampers which can be embedded to the real material and can exhibit a real good time, just like you see like with the minimum response time. And automotive and the aerospace, if the shock absorber of a vehicle suspension are filled with this MR fluid instead of the plain oil, then the whole device surrounded with an with whatever you see the like we can say electromagnet, the viscosity of fluid can be like enhanced, and hence the amount of damping provided by the shock absorber can be varied depending on the driver performance or we can say weight which is being carried by this vehicle. And also you see we can say that the dynamical variable in order to provide the stability control, these MR dampers are perfect. So, this is an effect of the magneto-rheological damper, for which we can say that the magnet ride active suspension system can be adopted, through which we can permit the damping factor which can be adopted or which can be adjusted you see here in every millisecond response according to the condition. So, they are so quick in their response. So, whatever the conditions are being changing, like the operating or we can say the boundary conditions, they can be immediately adopt and respond in corresponding way. So, that is why you see here wherever we require such kind of applications, right, from automobile to aerospace to helicopter damper, or even for the military and all other part, or even for you see in like where the human responses are requiring more, the MR damper can be straightway embedded to the system, and then you see here we can get such kind of things. So, even in the General Motors and other like various big companies, they are developing the magneto-rheological based clutch system for push button 4-wheel drive systems, because this clutch system can be used as you see like just the electromagnets to solidify the fluids, which can lock the entire driver shaft into the we can say the drive train, and whenever it is being required they can be engaged and disengaged accordingly. And Porsche has introduced, you see here in one of his paper, the MR engine mounts, which we just discussed in the previous case. Even the ER fluid can be also used as the engine mount, and at the high engine revolution these MR engine mounts get stiffer to provide a more precise gear stiffer field by reducing the relative motion between the powertrain and the chassis or entire body itself. So, they can be act as a good damper even for heavy machinery, and in the quick response time you see they can give the entire features. Though you see here there are various other models like the Lee model and various other models are more refined models are available, but you see here we need to restrict our this part because we need to feature it out that you see along with these like the flow characteristic of the magneto-rheological fluid, as we are just using the damper part, but we need to check it out that you see here all the time we cannot be replaced, because you see here the whatever the electromagnetic fluxes are being created, they can also affect the various other properties of the surrounding part. So, you see abruptly we cannot use these features for like controlling the vibration through the damper. So, you see here in the last two lectures, right, from ER damper to MR, means electro-rheological fluid damper, and MR this magneto-rheological fluid dampers, they have an excellent properties according to the resistance which is being like provided to the system, and it is absolutely based on the applied electric or magnetic field. And even you see they in nowadays you see here because of like their sensitivity and the quick responses, because their responses are in milliseconds only, though you see MR fluid is more quicker than the ER fluid, but since you see if we compare with the other sensor and actuation features, their response time is very fast. So, we can adopt these things, but again you see here we need to check it out that where it has to mount and what are the service and the operating conditions, so that there should not be any damage, because you see here they can be effectively used against the shock absorber, both the dampers, because they are showing based on their Bingham model characteristics, they are almost exhibiting the viscoelastic features, in which you see we have both before yield and after yield point there is a clear solid and liquid features are there. Means when the magnetic or electric field is on, they are almost exhibiting. When electric field is on, it is just exhibiting or like the solid features, in which you see here all the particles, the polarized particles are aligned in that direction where the resistance is being required, and you see all the like the field which is being there you see on outside, it should be perpendicular to that part. So, this is the basic concept you see and some general mechanism, but you see still more and more research is being going on according to like that where we require the clear configuration and the control of the dynamic forces, how we can adopt these electro-rheological or magneto-rheological fluid dampers. Now, in the next lecture we are going to discuss the another form of these application of this electro or magnetic field in the like the electrorestrictive and magneto-restrictive fluid this like the material part. So, how we can again you see here put the restrictive features by applying these magnetic and the electric field there itself. We are going to discuss in detail basic mechanism and their applications. Thank you.